Hi, my name is Charlie from Shanghai Jiao Tong University. I'm very happy to briefly introduce our work, Dapper, an adaptive manager for large capacity persistent memory. We know that many emerging data-intensive computing applications require very large memory capacity. However, the gap between computing capability and memory capacity is actually increasing these years. So it is very important for us to think about how to efficiently deploy large capacity memory systems. Persistent memory can be an excellent candidate for this purpose. Emerging PM module has very large capacity and DRAM-like performance. In this paper, we focus our attention on shared memory NUMA architecture, which is very popular among commercial servers. We try to build a hybrid memory system that shows very low performance overhead with minimum OS modification. Managing hybrid memory systems can be challenging. Actually, the cost for maintaining large capacity persistent memory is very high. For example, memory system accounts for over 20 to 30% of the total server energy consumption. Also, large capacity PM uses very large memory space to keep track of every memory page. For example, a 1 terabyte PM can consume up to 16 gigabyte space to store all page descriptors. In this work, we propose an adaptive manager for large capacity persistent memory. In our design, the DRAM space and the PM space are configured on each NUMA node to form a unified address space. A hide unit is designed to smartly initialize the PM space. A reload unit can allocate local memory space to handle memory pressure. We also define a PM volume device for enhancing the functionality of Dapper. Dapper is actually built on top of our prior work, AMF, which is published on HPC 2016-18. There are two major differences. First, Dapper adopted a new memory organization to evenly distribute PM modules across processor cores. Second, it uses a hybrid memory controller on each NUMA node to minimize remote memory access. Our design has three key features. First, it allows the kernel to hide the PM module during the boot stage, and therefore it does not require significant OS level modifications. It keeps PM module detectable but inaccessible on each local NUMA node socket. After the boot stage, Dapper monitors the consumption of memory space. Once a local node cannot satisfy the memory-intensive application, Dapper will automatically trigger a PM integration procedure to expand the capacity of local memory. We propose control schemes to avoid frequent remote memory access. Finally, we also propose a PM volume space management scheme to improve the usage effectiveness of PM. We leverage a persistence attribute of PM to overcome the torn sector problem. To evaluate our design, we build a 6-SKU down system that has 512 gigabytes memory and 32 cores. We compare Dapper with different baseline configurations. We first test two representative graph processing workloads. Compared to traditional approaches, Dapper shows 5% better performance on BFS and 13% performance improvement on SPEC. We evaluate SPEC CPU2006 as well. Compared with our baseline, Dapper can achieve performance improvement over 20% on both integer and floating point workloads. To sum up, we propose Dapper, a lightweight PM management framework for NUMA architecture. It is compatible with the existing DRAM system, and it is transparent to the application. We hope that Dapper can enable future systems to better exploit the benefit of large capacity PM with the slightest overhead. Finally, we want to thank IEEE for giving us this opportunity to share our work. We encourage you to read our paper for more details. Thank you.